take a look. I'm always going to try to stay ahead of you on the homework assignment. I've been working section 5, 6. I just got it done this morning. There's page 1. Page 2. Page 3. Page 4. Page 5. Page 6.
Oh, he told us he was waiting to get to the building.
And page 7.
I thought I enjoyed that section.
Yes. Well, since it's an exam, I could kill you with tons of questions.
Or
a few really hard questions.
Well, what I would say, Brian, is that I would emphasize the importance of section 5, 6, so you'll see more from that section than any of the others. Probably in order of hierarchy, 5, 6, 5, 1, and boy, the rest don't compare to those sections. So a lot of 5, 6, and a lot of... So 5, 1 is those Riemann sums, infinite summations, fun stuff. So that's important. The fundamental theorem of calculus, not as much, even though it's called the fundamental theorem of calculus. Some from 4.9 with the applications, some from 5.5 with the applications, but not as much. So now, to start off today, I want to look at one more problem out of section 5.5, and then we're getting to that section 5.6 with the substitution rule.
I think we're a different kind of gift.
What gifts do you see in this class?
The gift of personality?
There you go.
We're a special. Exactly. Number 16, guys. I worked all the odd problems in this section on the homework, and quite honestly, there's not a single interesting question out of the homework assignment for this. I was very disappointed. Section 5.5 took me all of 1 page to work. I said, come on. But this even problem here is superior to any of the odd homework questions. So I want to make sure we're comfortable with this one. Might you see something like 16 again? Yes. Is there anything like it in the homework? Unfortunately, no. And nor could I find anything in the odd problems. This one's talking about a marginal cost of producing X tablet computers is C prime of X. So that's the change in our cost function. Marginal cost is the incremental cost per item. So if you know that your costs are increasing by $100 per computer, hey, that's C prime of X is 100. In this case, C prime of X is a function of X. And then it says, what is the cost of producing 3,000 units if the setup cost is 90,000? And then it says, if the production is set at 3,000 units, what is the cost of producing 200 additional units? Okay, so when we go in and try to attack this question here, so section 5.5, number 16. It's telling me that the marginal cost, which is the change in cost, is equal to 120 minus 0.06x and then minus, I guess that's 4, is that 4? That's 4 zeros. Yeah, 4 zeros and a 1.
Plus.
Oh, thank you. Okay, so I have that as my marginal cost function. Now, my goal is to try to address that first question. What is the cost of producing 3,000 units? But notice, I can't just plug it in. This is the change of cost. I need to get to my cost function. Well, I know that my cost function would be the integral of this, so I can say, well, if I want to find the cost of 3,000 units, how about I integrate from 0 units to 3,000 units of C prime of X bar? And let's talk about what answer will this give us? This will give us the cost of 3,000 units minus the cost of 0 units. Now my question to you is, would this answer the first question? What is the cost of producing? Is this going to be the cost of producing 3,000 units? Good, Kevin. That's what I was afraid somebody would think, oh, this is the cost of 3,000 units. No, it's the cost of producing from 0 to 3,000 units. It does not take into consideration your setup cost. So you'd have to say, oh, okay, yes, this is the cost of from 3,000 to 0, but I'd have to add 90,000 to that because I don't have a way of factoring that $90,000 setup into the integration problem. So I'd say, whatever I get, I have to add $90,000. So I'll say, okay, the cost of 3,000 units is going to equal the integral from 0 to 3,000 of 120 minus 0.06x plus 0.00001x squared dx, and then I'll say plus 90,000 for the setup cost. This is just going to be the cost from 0 to 3,000. So now, the integral of this is pretty easy. So I could say, well, this is going to give me 120x minus 0.06x squared over 2, so that's minus 0.03x squared. And then I would get, this is going to be times x cubed, so I think just to keep it exact, I'll say plus 0.00001x cubed over 3. And we're taking this and we're evaluating it from 0 to 3,000. And I'll also add 90,000 to that answer. So I can say, okay, having my calculator assist here, what I'll do is I'm going to store 3,000 in for x. I'll say 3,000 store right above the on button, x. And so now my calculator is going to think x is 3,000. So I can say 120x minus 0.03 x to the second plus 0.1234 zeros a 1 x to the third divided by 3. This will allow me to evaluate the function at 3,000. I can say, so at 3,000 I get 180,000. I already know this evaluated at 0 is 0. So I'll get 180,000. I'll go ahead and show minus 0, just so you don't think I forgot about the lower limit, plus my 90,000. So I can say I know that the cost of producing the first 3,000 units is going to be $270,000. Now, the other part of this problem, so that's what is the cost of producing 3,000 units if the setup cost is 90,000? That's the answer to the first question. But then there's a second part here. If production is set at 3,000 units, so that's your already current production, what would be the cost of producing 200 additional units? So if I want to find out, well, the cost of 200 additional units, all I would need to do is evaluate the antiderivative of this function starting at 3,000 going up to 3,200. That's going to be the incremental cost of the next 200 units. So I can say, well, this is going to be my 120 minus 0.06x plus 0.00001x squared again, dx. We already integrated that to 120x minus 0.03x squared plus 0.0001x cubed over 3. So it's the same thing as I did last time, except now my limits of integration start at 3,000 and work up to 3,200. I already know that when I evaluated this group at 3,000, I had my 180,000. So that's going to be my lower limit of integration. So I'll say whatever that upper limit is, I'll be subtracting 180,000 from it. And now in order to get to that upper, notice I have the function entered in. What I'm going to do is say, I want to say 3,200 stored in for x. So now my calculator thinks every time I type x, it's 3,200. I'll go second enter, bring back up the expression. And so when I do that, 3,200 evaluated into this is going to give me 186,000. 026. And since we're talking about money, you need to round to 2 decimal places, 67 cents. So we could see that your increase in costs, if you want to produce an additional 200 units, you'll have an increase of $6,026.67 increase in cost. The only thing that differentiates this problem from the other ones in this section is it has that setup cost that you have to account for in the problem. The rest of them just work out directly. Yeah?
But for the other 200 units, wouldn't be a additional setup cost?
No, because, so according to this problem, once you're set up for the day. You don't have to worry about it. You don't repay that ever again. But now in reality, of course, your facilities will break down more quickly if you produce more units. So probably is some additional setup fees. But just sticking with the equation. Okay. We're ready for section 5.6. Integration by substitution. One of the ways that you measure students at the end of a Calc 2 course as far as did they learn what they needed to learn out of Calc 2, probably, if it's not the most important, it's at least one of the top 3. Do you know how to integrate effectively using the technique of substitution? And I am guaranteeing you that the answer will be an emphatic yes if you get through this class. Because we're going to make sure you see every type of substitution problem. I'm not just going to do the wussy problems. We're going to look at problems where you have to do double substitution. We're going to be doing trigonometric substitution, all these fun different techniques. And fun means fun in this case. I think you'll agree. But now, so starting off 5.6, substitution. Now, notice in Calc 1 we had rules. There's no such thing as a substitution rule. It doesn't always work. It's the substitution technique or substitution method. So you say we're integrating by the method of substitution. There are no rules in Calc 2. So I'll say right now we cannot integrate something like the following, but substitution makes it very, very simple. I'll say, what if I have the integral of 2x on the square root of 1 plus x squared? Now, if you've ever seen substitution before, you already know, hey, that's a ridiculously easy problem. It is. We're going to work to ridiculously difficult. But now, in this one, the problem is we don't have any techniques to say, well, this is the term 2x times this square root. There's no such thing as a product rule for integration. I can't just say, well, integrate the first term times the second term plus the first term times the integral. You can't do that. So we're left with trying to think, is there some way I can simplify it and then integrate it with techniques that I already know? And the answer to that is yes. So what we do is we introduce another variable. And the variable that I want to introduce, usually we call it a U-Substitution. Let U be whatever's inside of a function in the problem. And so in this case, the clear choice, and it becomes more clear as you get used to this, the clear choice for U is this. Why? Because it's inside of a function. The function is the square root. So I can say, let U equal what's inside the square root. So I'll say, let U equal 1 plus x squared. Okay. Now think with me about this. If I said, I want you to take the derivative of the function U, say, well, U is a function of x. So its derivative, you could call it U prime of x, or hopefully you're used to the Leibniz notation, du dx. The derivative of U with respect to x would equal 2x. Okay. Now, in Calc 2, we typically don't want the full derivative du dx. We want just the differential du. So please remember, this du dx, what does it mean? It means the infinitesimally small change in u over the infinitesimally small change in x. It is legitimately a fraction. You need to start getting used to treating it as a fraction. So if I say, I want you to solve for du, you can say, well, du is equal to 2x times dx. Okay. Now, notice over here in my problem, I have a 2x dx in the problem. There's my 2x, there's my dx. The whole point, this is called substitution, is I'm going to try to substitute what I've set up over here back into the problem to create a problem that we're comfortable integrating. So I can say, okay, this is equal to the integral. Order of multiplication is irrelevant. So I'll say this is the same thing as the square root of 1 plus x squared times 2x dx. Which now, using my substitution, I'll say, well, the square root of 1 plus x squared. I'm saying that 1 plus x squared is u. So this is going to become the square root of u. What's all of this going to become? Du. That's what we do. So you'd say, okay, if I have the integral of the square root of u du, now it's just power rule. You say, well, this is the integral of u to the 1/2 du. Now we integrate. Power rule says add 1 to the exponent, u to the 3/2, divided by that new exponent, multiply by 2/3, plus your constant of integration. Then you can say, okay, you don't want the final answer in terms of u. No, I don't. So once you integrate, then you can back substitute. We know u is just 1 plus x squared. I can say this is 2/3 times the group 1 plus x squared plus c. Oh, 1 plus x squared to the 3/2 power plus c. And then you're thinking, hopefully, but the original had radicals, so your final answer has to have radicals. Yes. So you weren't thinking that? I'll say 2/3 on the square root of the group 1 plus x squared cubed plus c. Final answer. So all I've done is I took a problem that didn't know how to integrate in that form. It was not in a form where I could use my power rule. So I said, let's somehow use substitution in order to get it into a form where I can use my power rule. And the way I did that is I just looked, well, this group inside the square root looks overly complicated. Let's simplify it by just calling it a different variable u. And then I can say, well, if I call that u, the derivative of u with respect to x is 2x. So then du is 2x dx. It worked out nicely in this case because the other terms I had in there, 2x dx, became du. And then I just had the square root of u underneath the radical, which allowed me to use my power rule to simplify. Now, in general, every single time, our method is going to be the following. So I wanted to work a problem before officially stating the method, because sometimes when you state the method without an example, people are like, what? That doesn't make any sense. The substitution method is the following. It just says that if u is some function of x, so I'll say if u is g of x, that's some function of x. In our case, u was the function 1 plus x squared. That's a function of x. Is a differentiable function. Which, remember, almost everything is differentiable. It'll have to be differentiable in order for it to be integrable. So if that is a differentiable function, then I can say the integral of f of g of x times g prime of x dx is equal to the integral of f of this function evaluated at u with respect to u. Now, what this is doing, please notice in here, f of g of x. What's the function f in this? It's the square root function. G of x is the group 1 plus x squared. G prime of x has to be multiplying that f of g of x. G prime of x, the derivative of g of x would be 2x dx. So I'm saying all I had to do was rewrite it as f, which is the square root of u. That's why I use inside the square root du. So everything I just did follows straight into this. Although I understand if you're like, I'm not quite sure I get that definition. What we just did fits the definition. Now, I think the more we work, the more comfortable you're going to get with it. This will be my first real full example. I'll say, what if I have the integral of x cubed cosine of x to the fourth plus 2? So, unlike my first, I'll call it pre-example problem, everything in that problem worked out absolutely perfectly. This one, it doesn't work absolutely perfectly, but that's absolutely okay. And I need you to see why. First of all, you need to get comfortable saying, I know what u is in the problem. U is going to be what's inside the function. I have a cosine function. What's inside of it? X to the fourth plus 2. So I'll say, if I let u equal x to the fourth plus 2, then du, and if you want to do du dx, you can say the derivative of u with respect to x would be 4x to the third. So du is 4x to the third dx. Of course, it's best if you can go directly from here to here. One of my pet peeves in these problems is students who are kind of sloppy with their notation, and they say this. Du is 4x cubed. And they'll say, oh, you knew what I meant. Yeah, I know what you meant, but that's wrong. Du is not 4x cubed. Du is 4x cubed dx. Okay? That has to be there, guys. So now, when you think about this, you say, do I have what I need in my problem? So all of this is going to become the cosine of u. That's fine. But in order to do that, I need to have it du. So I need to see a 4x cubed dx in there. So what I'm going to do is say, well, I'm going to rewrite my problem, and I'll put a 4x cubed dx in there. You can always multiply by a constant on the inside if you multiply by the opposite of that on the outside. And in fact, in order to save yourself some work on your paper, it's probably better if you just go ahead and do this instead of having to rewrite the whole thing. Now, when you look at the homework that I've done for this section, you'll notice I've shown it out in detail. I'll go ahead. So like, for example, in number 11 there, you'll see that I needed to multiply by -8 in there. So I show it out. I multiplied the inside by -8. I divided -8 on the outside. So I showed it fully. I didn't just go up there because I thought I'd lose some people. But now in here I'll say, okay, I needed to see a 4x cubed dx. So everything I underline is going to become du. X cubed times 4dx, all of that is du. This becomes the cosine of u. So I can say this is going to equal 1/4 the integral. Cosine u, all of that is du. Once you get that, you can do the integration. You can say, well, the integral of cosine. I know derivative of sine is cosine, integral of cosine is sine. This is going to give me 1/4 times the sine of u plus c, like that. Then we say, well, okay, the final answer needs to be back in terms of your original variable. U is nothing more than the group x squared plus 4. So I'll say, final answer is 1/4 the sine of x to the 4th plus 2 plus c. I did. 1/4 c is c.
C is all numbers.
Yeah. Aha. Yes.
So for these, we're not solving yet the constant of integration yet. We're not solving. We're just leaving c.
Yeah. We're leaving. There will be definite intervals in these as well, but for now, I'm looking at indefinite intervals. Yeah, in your homework set, like the first 1 through 60 is indefinite intervals, then they throw definite intervals in at the end. But we're going to look at those today too, I think. Okay, so a second example. What if I ask you, I want you to evaluate the square root of 2x plus 1, and I'm asking you to integrate it with respect to x. Say, well, the choice for you is pretty clear-cut. Say, what's inside the function? 2x plus 1 is inside the function, so I'll say, let u equal 2x plus 1. So, the derivative of u, du, is going to be 2 with respect to x. So, 2 dx. So, I needed to see a 2 dx in there, and I don't see it. I'll show my work a little better this time and say, well, all I would have to do is rewrite my integrand and say, I already had the square root of 2x plus 1. That's fine. But I needed to see a 2 dx in there in order to be able to call that du. Well, I'll say times 2 dx. But I can't multiply the inside by 2. That changes the value. So all I have to do is say, well, multiply the outside by 1/2 then. Or just say divide the outside. So now everything is set up for the substitution. I'll get 1/2 the integral, the square root of 2x plus 1. The whole point to this substitution was so that I could write it as the square root of u. So I'll say square root of u, all of that is du. You'll notice a lot of these problems, once you get down to the final step, pretty easy to integrate. It's just a matter of setting it up. I'll get 1/2. This is u to the 1/2, so it becomes u to the 3/2 times 2/3 again. Plus c. So now final answer. 1/2 times 2/3 is going to give me 2/6, which is 1/3. U is the group 2x plus 1. I'm going to go ahead and put it in a radical. It's going to be the square root of the group 2x plus 1 raised to the third power plus the constant of integration. And again, remember, c is just any number, so it sounds silly to say 1/2 c. 1/2 c is c. Does this seem pretty straightforward so far? It's okay. All right. What if I look at a problem like the following? I want the integral of x over the root of 1 minus 4x to the second dx. The problem I always have with Calc 2 is I remember so much about derivatives, and to me, as soon as I see the square root of something minus x squared in the denominator, I'm thinking, oh, it's an inverse sine function, because the derivative of inverse sine is 1 over the square root of 1 minus x squared. So I'm thinking, no, this is some version of inverse sine. It's not. And we need to show that it's not. So in trying to work backwards, the way we would do this is you just say, what's inside of the function? I'll say, well, inside of the square root is the group 1 minus 4x squared. I'll try that. So du, the derivative of 1 minus 4x squared, that's going to be negative 8x dx. So now, I'm going to show it in a different color as I go back in there. I'm thinking, okay, in order for me to do substitution here, I absolutely must see a negative 8x dx in there. I see an x dx. So all I have to do, put a negative 8 right there. But I can't multiply the inside by negative 8 unless I make up for that by dividing the outside by negative 8. So I do that, and now my problem is set up. I can say this equals, I'll say negative 1 over 8 times the integral. This negative 8x dx, remember, all of that becomes du. Personally, I like to write that out over here. So I'll have a 1 du. Could you put the du in the numerator? Sure, you could. I like it out there myself. So I'll say I have 1 du is all of that. The square root, well, that becomes the square root of u. So now we can say this is negative 1 over 8 on the integral u to the negative 1/2 power. 1/2 power since it's square root, negative since it's in the denominator. So I'll say this is going to equal negative 1 over 8 times the group. Integrate this function. When we integrate it, we add 1 to the exponent. So this becomes u to the positive 1/2 power divided by 1/2. If you divide by 1/2, you're multiplying by 2. So I can say this is going to become 2u to the 1/2 in there. Plus c. So I can say, well, I know when I multiply that 2 by the negative 1/8, I'll get negative 1/4 square root of u plus c. And I could have went ahead in the same step and substituted back in for u. You'll have to do that in your last step. If the problem's written in terms of x, your answer has to be in terms of x. So I'll say, well, this is negative 1/4 on the square root of 1 minus 4x squared plus c. Yeah, go ahead. Because negative c and c is the same thing. Remember, c just stands for any number. So it could be negative 4,368. It could be positive 2,512. So c is just the integrational constant. That's why I am never, ever, ever distributing through and saying Oh, well, that's 1/2 c. 1/2 c is c. I need you to see that. Number 4. Oh, this one should be a quick one. It's not very fun. But we do need to make sure we look at exponential functions as well. So, whenever we did the derivative rule, we said, well, the derivative of any exponential function is that exponential function times the derivative of its exponent. We've already actually integrated functions like this too. We said, well, as long as that exponent is linear, then the integral of any exponential function is that exponential function divided by the derivative of its exponent. So just from that, we should know that our answer is e to the 5x divided by 5 plus c. All I want to do is show, even on this easy problem, substitution still works. You'd say, what's inside the function? Well, the function is e to the x, but instead of e to the x, you have e to the 5x. So you say, what's inside the function is the 5x. The derivative of that, derivative of u, is going to be 5 with respect to x. So I would look at this and say, in order for me to work this problem, I need to see a 5 dx on the inside. So I'd say, well, multiply the inside by 5 then. If you do that, you have to make up for it by multiplying the outside by 1/5. You can always multiply a constant. And so I'll say, okay, I'll get 1/5 times the integral. This is just e to the u. And then this is du. So now I can say, well, the integral of e to the u is e to the u. So I'll get 1/5 e to the u plus c. And I'll say, well, that's 1/5 e to the u, which is 1/5 e to the 5x plus your constant of integration. Now, with this problem, please do keep in mind, we had other techniques to do it, but substitution worked. Hypothetically, guys, would we be able to attack this problem right now? Could I use substitution on it?
Can you double substitution?
Not so I need you to see when substitution will work and when substitution will not work. This is a clear, it's not going to work. Why? Well, because you'd say, well, let u equal x squared. So let's say, well, if u, so this is not going to work. Du would be 2x dx. I need to say, well, I need to see a 2x dx in there. Could I multiply a 2 on the inside and a 1/2 on the outside? Certainly. Could I multiply by an x on the inside and x? No, that's a problem. So I can handle the 2, no big deal. But I can never just say, oh, go ahead and just multiply by an x on the inside of the integral and divide by an x. That's impossible. You can't do that with variables. You've got to find some other scenario. This problem, unintegrable.
Can you not substitute with another u?
Nope. Different u, double u. Yeah, that's what I always do. When I do double substitution, it's u and w. But wouldn't help. Okay. So, how about if I ask you to integrate the tangent of x with respect to x? It looks so simplistic. This is not one of our functions we should know right off the top of our head, though. Because you say, well, I know what the derivative of tangent is secant squared. But I don't know the derivative of what is tangent x. Don't know. So I have to think of some way to figure it out. And what I'll do is I'll say, right now it's not set up for any U-substitution, because you say, well, is it going to help if I let what's inside the function be u? If If I let u equal x, then du is dx. You've just turned the problem from tangent x dx to the tangent u du. Like, woohoo! Really gone so far there. Wouldn't help at all. So I have no question. I must rewrite this one. I have to. So I'll say, okay, tangent is sine over cosine. Ah. Ooh. And you might still look at this and say, but what's inside the function is x. And it's not going to help if I just interchange my variables u to x. So if you think, well, okay, another common choice for u is whatever's in the denominator. And if you're thinking, okay, how am I supposed to know it's what's in the denominator and not what's in the numerator? Because if you think about that, if I said, so hypothetically, this would be the bad choice for you. If I said, let u equal your numerator, u equals the sine of x, then du is the cosine of x dx. Do I have the cosine of x times dx in this problem? You should see, no, you have dx divided by the cosine of x. So I know that whenever I take the derivative, it's going to be multiplication. If I let u equal what's in the denominator, then the derivative of cosine of x is going to be negative sine of x dx. Well, I have sine of x dx in there, and the negative is going to be easy to take care of. So I have no doubt I need to let u equal the cosine of x. So du, derivative of cosine is negative sine of x with respect to x. So I'll say I need to see that negative in there. I'll multiply by a negative on the inside. I'll multiply by a negative on the outside. So I'll say this is equivalent to a negative integral, negative sine of x dx. All of that becomes du. So my numerator is just 1, and I'll have a du over here. My denominator, cosine of x, u. We know what the integral of 1 over u is. Remember, this is the exception to the power rule. You can say u to the negative 1 power. You're not going to say it's u to the 0 divided by 0. This is natural log of u. So I'll say this is the negative of the natural log of the absolute value of u plus c. Okay. So now if I simplify this, I'll get the negative natural log. In the place of u, I'll have cosine of x plus c. Now, you might notice, let's see, you have a table of integrals, and some teachers let their students integrate by using this table of integrals. That'd be terrible. Takes the fun out of it. But notice on this table of integrals in the back, your number 11 says that the integral of the tangent of u du is the natural log of secant u plus c. Is my answer wrong? Go ahead. What were you saying? Well, yes and no. What can I do with that? I heard somebody say the negative. What can I do with that negative? It's a negative 1 coefficient. What do you know about the coefficient of any logarithmic function? It can be up as an x. Nice! So I can say this is understood to be negative 1 times the natural log of cosine x. So I can say, well, that's the natural log of the cosine of x all to the negative 1 power plus c. What's the reciprocal of cosine? Secant. This is the natural log of the absolute value of the secant of x plus c. Is one answer better than another? Nope. I just wanted to show that they were the same. But it's cool, though. Oh, okay. I got you here.
Question.
Yes.
I know we don't write it because it's c, but if c was an actual number in this problem or whatever, in the future, that -1 exponent would go to C as well, right?
No, because the C is not part of the natural log.
Okay.
Okay, so now, of course, technically the -1 would get distributed to, you have minus C,
Okay.
but minus C is plus C. Okay, so if I look at, this was the question earlier. What if we have definite limits? It makes it a little bit more interesting. Let me show you. If I have the integral from 0 to 4 of the square root of 2x plus 1 dx. Couple of different ways to do this. I'll do it the way the book, the only way the book does it. I'll do it that way, and then I'll mention the other way. So we follow the U-Substitution just like we've done on every other problem. You say, what's inside the group? Let it equal U. So U equals 2x plus 1. du is going to be 2 dx. So I know in order to work this problem, before I do anything else, I need to see the 2x plus 1 in there. Yeah, I do. And I need to see a 2 dx. I don't see the 2 dx, so I multiply by 2 on the inside. I multiply the outside by 1/2. That's always workable. But now, those limits of integration, I need to work with them. Because if I want to evaluate this in terms of u, I can't leave my limits of integration in terms of x. So, no problem. I just say, if I evaluate the lower limit in the function u, I'd say, well, that's going to become 2 times 0 plus 1. That lower limit of integration becomes 1. What about the limit of integration 4? I'd say, well, u of 4 is going to give me 2 times 4 plus 1. 8 plus 1 is 9. So now I could say this is equal to 1/2 on the integral. No longer is my limits of integration 0 to 4. It's 1 to 9. And then on the inside, the square root of 2x plus 1 becomes the square root of u. And 2 dx becomes du. Now, please keep in mind, it would be absolutely wrong. You could say, oh, well, what if I don't want to change my limits of integration? Put it back into terms of x at the very end and then evaluate from 0 to 4. I would still have to count off if you did that. That is terrible. That's saying it's equal to the integral in terms of u from 0 to 4. No, it is not. So, can't do that. I'll talk about the other way in a moment, though. Right now, I changed my limits of integration. Have to do 1 to 9. So now I'd say, well, okay, this is equal to 1/2 times the group. Seen that before. U to the 1/2 becomes u to the 3 over 2 times 2/3. No longer do we have to worry about the plus c, because the c is going to cancel out in your upper and lower limit anyway. So you just say, evaluate the function from 1 to 9. And I'll say, well, okay, this is going to be 1/2 times the group. And something that I would recommend you do, instead of saying 1/2 times the group, any constant can always be factored out. You'll make your work a little easier if you go ahead and factor that out. So I'll say, well, 1/2 times 2/3 is going to be 1/3 times the group. And I'll say, I need to evaluate this at 9. So I'd say, well, that's the square root of 9. Square root of 9 is 3. 3 cubed, 27. So when I evaluate it at 9, I get a 27. When I plug the 1 in there, the square root of 1 is 1. 1 cubed, still 1. So when I evaluate at the upper limit, I got a 27. Evaluate the lower limit, I got the 1. So I'll get 1/3 times 26 for just 26 over 3 for your final answer there. This is the method that the book will use. Alternatively, if you wanted to, if you're thinking, I don't want to have to worry about changing the limits of integration. I just want to integrate the problem, put it back into terms of x, and then evaluate it in terms of x. Okay, so what I would have had to do is say, my problem was 1/2 the integral 0 to 4 square root of 2x plus 1, and I put the dx times 2 out there. Okay. So if I want to use a U-substitution, I still can. I can say, so this gave me 1/2 the integral square root of u du. So you can still do that. Please notice what I've done though. If I know I do not want to evaluate this in terms of u, do not put any limits of integration there. You don't need to find them in terms of u if you never intend to evaluate it in terms of u. So just leave this part blank. If you put 0 to 4 here, I would count off. That's wrong. So I just leave it blank. I integrate it in terms of u, and so I get my 1/2 times 2/3 u to the 3 over 2, which I can say, well, that's going to give me my 1/3. Put it back into terms of x. U was nothing more than the group 2x plus 1 to the 3 over 2 power, and then say, evaluate this answer from 0 to 4. Some people like doing it this way better. I would say the majority prefer just going ahead, changing into terms of u, and never having to worry about getting it back in terms of the original variable. Notice, it's the same thing either way. It's the same amount of work, because now, what do I have to do? I have to say, well, plug a 4 into here. When you plug a 4 in, notice what happens. 2 times 4 is 8, plus 1 is 9. You're evaluating this function at 9. So you're doing the same work. So you'd say, well, I would have 1/3 times 9 to the 3 over 2 power minus 1/3 times, when I plug a 0 in there, 2 times 0 is 0, plus 1, 1 to the 3 over 2 power. So I would still get my 27 over 3 minus 1 over 3 for 26 over 3. So if you want to do it this way, I'm fine with that. Our book will do every single problem this way. That's how I'll do it in the homework assignment as well. But I'm just saying, if you don't like this step right here, then leave off the limits when you put it in terms of u, integrate the problem, put it back in terms of x, and then evaluate at the original limits. You get the same answer. Okay, now, and whether or not you ever do it this way, it's important that you at least remember, oh, yeah, you can do it either way, because different books, different authors, some authors do it exclusively that way, some will do it this way, and then others use both techniques. So you at least need to be having seen it before. Okay, number 7. What if I give you the definite integral from 1 to 2 of dx over 3 minus 5x quantity squared? Is the choice for you in these problems always obvious, guys, so far? You'd say,
except for the sin x over cosine.
yeah. So on this one, you'd say, choice for you is obvious. It's going to be 3 minus 5x. So du is going to be negative 5 with respect to x. Before I worry about my limits of integration, I'm going to go back and make sure this problem works. I need to see a negative 5 dx on the inside. So I'll say, well, that means I need to multiply the inside by negative 5, which means I need to divide by negative 5 on the outside. So I'll say, okay, now the problem can have a U-substitution. When I do the U-substitution, I'll also change the limits of integration. The limit of integration 1 is going to become 3 minus 5 times 1. So that lower limit of integration is going to become 3 minus 5, negative 2. The upper limit of integration, which was 2, becomes 3 minus 5 times 2. 3 minus 10, negative 7. So we're going to say our problem changes to negative 1/5 on the integral. No longer from 1 to 2. Now we're starting at negative 2 and going to negative 7, right? So we're actually going backwards. So on the inside, this negative 5 dx is all du. So I'll say all of that is du, or you could have put it over here, put a 1 in your numerator. My denominator is going to become u squared. So I'll say I have my negative 1/5 in front, ready to integrate the inside. The inside is the same thing as u to the negative 2. So we say when we integrate that, it's going to become u to the negative 1 over negative 1. So I would rather simplify that here. U to the negative 1 over negative 1. That's going to be negative 1 over u to the 1. And then I can say plus c. So now, I'm evaluating this from negative 2 to negative 7. And I'll say, okay, I'll have negative 1/5 times the group. When I evaluate, that plus c, sorry, I accidentally put that in there. It's not wrong to put in there because you just have plus c in your top limit, and then you'd be subtracting c in your bottom limit. So it's going to eliminate itself, but it's better not to put it. So I'll just say this is negative 1 over u, evaluated from negative 2 to negative 7. So I'll say negative 1 over negative 7 minus negative 1 over negative 2. That's a lot of negatives. And so I'll say on the inside, I'll get positive 1/7 minus 1/2. Common denominator on the inside of 14, I would have this is negative 1/5 times 2 over 14 minus 7 over 14. Gives me inside is negative 5 over 14. I'd have negative 1/5 times negative 5 over 14. A negative times a negative is a positive. The 5's eliminate. I get a positive 1/14. Now, keep in mind... Oh, sorry, go ahead. Questions? No. So, yeah, I accidentally had a plus c in there. But now keep in mind, that it would be this term plus c minus this term plus c. So I would have a c in this term, I'd have a c in this term. The c's would cancel. Now, if I did this, check this on the calculator just real quick. My original problem was just 1 over the group 3 minus 5x quantity squared. So I could say math 9. And I'm kind of checking them sporadically, but with definite intervals, it's probably in your best interest to check it every time. So I'll say it was 1 over the group 3 minus 5x quantity squared, comma, we're integrating with respect to x, comma, your lower limit in terms of x was 1, and your upper limit, comma, was 2. This should give me 1/14. I think 1/14 as a decimal is like 0.07142857. It's a repeating decimal. Yes. 0.07142857, 142.857, 142.857. Let's see if it converts it to 114. Yeah. Okay.
So we could have done that with the alternative method by paddle.
Say that again.
With the method that you
The bottom has to be LCD.
Oh, well,
Yeah.
you would have had to leave it clear in this step. You wouldn't put any limits of integration at all. And then once you got to, again, you wouldn't have any limits of integration at all. After this step, you'd have said, well, that's going to be, I'll factor out the negative 1. 1/5 times 1 over u would become 1 over, what is u equivalent to? 3 minus 5x. I would be evaluating this in terms of x from 1 to 2. That's what you would do. And notice it's going to be the same thing. When I plug a 2 in here, I'd say, well, that's 3 minus 5 times 2. 5 times 2 is 10. Hey, that's 1 over negative 7 times 1/5. 1 over negative 7 times 1/5. It's going to give you the same thing. 6 of one, half dozen of the other. Question? Yes.
How does he get the negative 1 in the additional brackets? The negative 1 would be?
That's in your integration here. This is 1 over u squared, which is equal to u to the negative 2. Power rule of integration says increase the power by 1, divide by that new exponent. If I have u to the negative 1, that u to the negative 1 belongs in the denominator. Instead of doing that, I just said, well, that's the same thing as negative 1 over u. Okay. Number 8. This is what I would say my last one of the standard problems. Every problem after this is going to have a difficult twist to it. So this is the last of the nice problems. I want to make sure I cover every possible scenario so you're not, so when, as you're working the problems in the homework, you don't say, hey, he didn't do anything like that. In this problem, is it obvious what we need to call u? And it may not be obvious. You never achieve anything by just saying u is x. That's pointless. Because if I let u equal x, then I have the natural log of u over u. Every bit as hard. Natural. And if you think, why would you want to let it be the natural log of x? If you think ahead in your mind, derivative of the natural log of x is 1 over x with respect to x. Do I see a 1 over x dx in this problem? Yes, I do, right there.
No, don't.
So, you didn't. You do now. Yeah, if I ever made that mistake on a test, you'd just say, no solution. You didn't give me an integral, a variable to integrate with respect to. Oh, that'd be terrible. So, natural log of x dx, so I could say, well, u is going to be the natural log of x in this problem. The derivative of u, derivative of natural log of x, is 1 over x with respect to x. So, I see I have a dx over x right there. All of that is going to become du. And then I know that natural log of x is just u. So this is going to work out the u-tifully. But I'll say, well, I need to evaluate my limits of integration. U evaluated at 1. I'd say, well, that's going to become the natural log of 1. And we're supposed to remember natural log of 1 is 0, because any number to the 0 power is 1. The natural log of e, that's my second. U evaluated at e is the natural log of e. Natural log and e are inverse functions. They cancel one another out, and you're left with the exponent of that e, which is 1. So I can say my new integration problem, my lower limit of integration is 0. My upper limit of integration is 1. Natural log of x becomes u. Everything else in there becomes du. So this problem simplifies real nicely. Just the integral from 0 to 1 of u du. Now when we integrate that, power rule says 1/2 u squared we're going to evaluate that from 0 to 1. So we'll get 1/2 times 1 squared, just 1/2. When you evaluate it at 0, it doesn't amount to anything. So our answer is 1/2.
You do it the other way.
Yeah. So if you did it the other way there, Clint, you'd be at this step right here. So I just say, you do everything I did up there. And at this step right here, you would not have had to done that. And you'd have said, it's still the integral of u du without any limits of integration. And said, well, that's equal to 1/2 u squared, which is equal to 1/2. Then you'd have put back in what u is. U is the natural log of x. Then you're integrating that in terms of x, which is 1 to e. So here's what I was trying to say is that it doesn't matter which way, you're going to be doing the same work either way. It's probably a little bit more straightforward just to go ahead and change your limits of integration up front, because now, whenever I try to evaluate this, I'll get, well, 1/2 the natural log of e quantity squared minus 1/2 the natural log of 1 quantity squared. So in this one, I know natural log of e is just 1. So I have 1/2 of 1 squared, 1/2, minus 1/2 natural log of 1 is 0. So either way, I get my 1/2. Is that okay, Clint? Okay, now, some more interesting cases. Not necessarily more difficult, but more interesting. What if I'm going back to an indefinite interval, so we'll have a plus c in our answer. If I have the integral of x times x plus 1 to the 9th dx. Okay, so one way to work this, it's not the efficient way, but one way to work it is you could use Pascal's triangle or binomial expansion to think about what in the world is x plus 1 to the 9th. You could do that. Remember, if I'm trying to use Pascal's triangle, I can say 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. I'd have to do that out to the 9th power and say, oh, okay, so that's x to the 9th plus something, x to the 8th, plus all the way on down. Not the prettiest thing. And then after I did that, I'd have to distribute the x and then integrate all 10 terms. Kind of long. It'd be correct, though. So I'd say, I don't want to do it that way. That's not the efficient way. The efficient way is to use substitution. Substitution's not that, well, I don't want to say it's hard. It doesn't work as our other problems do. You let u be what's inside the group. Clearly, what's inside the group to a power is x plus 1. But this time, du is nothing more than 1 dx. So du is dx. So if I try to integrate my problem, I can say, let me just go ahead and set up my integral as it is now. I don't have anything to get rid of this x. I'll put it in there for now. This group becomes u to the 9th. And du is dx, so I have the du. Okay, so your problem is, you said, well, you can't integrate with respect to u if you still have an x in there. Most of the time, and especially if your book's giving you a problem like this, there's got to be a way to get rid of the x. There has to be. And there is in this scenario. In the one I worked earlier, I think I had an e to the x squared. That one was not possible. You could not do it anyway. This one is possible because notice right here. We want this to be in terms of u. I have an x in there. Well, I have x plus 1 is u. So solve for x. X is equal to u minus 1. So now I could just say, this is the integral, substitute in the place of x, u minus 1, times u to the 9th du. Oh. Now, here's the problem. Some students would say, well, you're just as bad off now as you were before. And I would say, oh, you are not looking at it correctly if you think that. Because up here, I would have had to expand a binomial to the 9th power. Not a very fun thing to do. Here, it's simplistic. All I have to do is distribute the u to the 9th through that group. And it works beautifully. I'll say u to the 10th minus u to the 9th du. Then we can use the power rule on each term. And I'll say, well, okay, this is going to become u to the 11th over 11 minus u to the 10th over 10 plus c.
So why can't we just subtract the u's and u?
Oh, that'd be terrible. They're not like terms.
Oh.
I didn't want to say it. Sorry. So just like you can't say x squared from x cubed, they're not like terms. So now at this step, all I would do is say I need to substitute what u is. So my final answer I'll write as x plus 1 to the 11th over 11 minus x plus 1 to the 10th over 10 plus c. QED. Ooh, I went through my 11 there, but you see what it is. Okay, now I want to do a problem like that one, but I want to increase the difficulty. Why? This is another scenario in which substitution needs to be used, but it doesn't work directly. We have to do some algebraic finagling to get it to work. So we say, again, the clear choice for you is 4x minus 1. And so du is equal to 4 dx. Okay, so I know I could get the 4 dx in there by simply, I'll multiply the inside by 4, multiply the outside by 1/4. That takes care of that part. So I could go ahead and work with it from what I know at this point and say this is equal to 1/4 the integral. I haven't gotten rid of that x yet, I will. On the square root of u, and 4 dx is simply du. So I'm down to that part. And I can say, well, okay, I need this whole function to be in terms of u. So I have to get rid of x. Well, I have a function right here relating x and u. So I just said solve for x in this equation. So I'll say u plus 1 is equal to 4x. So x is equal to u plus 1 over 4. It would even be better if you went ahead and distributed that 4 into the numerator and said, well, x is equal to 1/4 u plus 1/4. That's what I want to substitute in for x. So I'll say, okay. This is going to be, I already have a 1/4 on the outside, and then the integral of 1/4 u plus 1/4 times the square root of u du. I still can't integrate a product, so I'll distribute the u throughout this group, and I'll say this is 1/4 the integral. My first term, 1/4 u to the first times u to the 1/2 1/4 u to the 3/2 power and then of course the second one is just going to be plus 1/4 u to the 1/2. All of that, guys, is going to be integrated with respect to u. So I can say, okay, I'll have my 1/4 on the outside. On the inside, whenever you integrate this first term, it's just power rule. U is going to go to the 5/2 power. You'll be multiplying the front by 2/5. I'll show that out. I have a 1/4 times 2/5 u to the 5/2. And then I'll have plus 1/4. This u is going to go to the 3/2 power, so I'll multiply by 2/3 in front. U to the 3/2. And since I'm integrating and it's an indefinite interval, I'll have to say plus c. And then I can say, well, okay, I'm going to go ahead and take care of all my coefficients. In this first one, and I'm going to also distribute the 1/4 at the same time. I'll have 1/4 times 1/4 times 2/5. So that'll give me 4 times 4 is 16 times 5 is 80. 2/80 reduces down to 1/40. And then I'll have my u to the 5/2. The next one, again, the 1/4 distributes. I'll have 4 times 4 times 3 in the denominator. That's 16 times 3 is 48. Have a 2 in the numerator. It's going to reduce down to 1/24. And I'll have my u to the 3/2 plus your constant integration.
Wouldn't it be easier just like steps up, just take the 1/4 out and multiply it?
It would be. Yeah, I thought of that after I said this, and then I already put it in over here. I thought, well, guys, and I didn't want to backtrack myself because you're like, well, which way is he going to do it? But the easier way, kind of like you said, if I hadn't distributed that and I just realized I'm going to have another factor in there divided by 4, I could have just pulled it out and had a 1/16 in front and just had the square root of u times u plus 1. But I realized that after I'd already done that, and I didn't want to backtrack, and you think, what's he doing? So this works, but you're right. So here, I'm getting to my answer, and I can say, okay, I know u is 4x minus 1, so my final answer needs to be 1/40 on the square root of 4x minus 1 to the 5th Remember, if the original is written in radical, your answer needs to be in a radical. Plus 1/24 on the square root of 4x minus 1 to the third. Plus c. That's what it would be. Okay, the problems that we've been working so far, hopefully you thought they're woefully absent of trigonometric functions. So we need to fix that. I think maybe only one or two have had a trig function in it. What if I look at something like the following one? This one should be easy. It's a standard. This is a standard substitution problem, which means there's no algebraic manipulation needed. It works directly. If I have secant squared theta times e to the tangent of theta, d theta. Thinking about that, is it obvious what the choice for u needs to be? Yeah, u needs to be inside of a function. So one choice for u would be, you might say, well, secant's inside of a function being squared, but the derivative of secant is secant tangent. I don't see a factor of secant tangent in there. So I say, well, my other trig function that's inside of a function Tangent is inside the exponent of an e. Derivative of tangent is secant squared. So I can say, that's fantastic. I have a factor of secant squared. So I let u equal the tangent of theta. So du can be secant squared theta d theta. And this problem works very quickly. All of that becomes du. So I'll say this is nothing more than the integral of e to the u du. And the integral of e to the u is e to the u plus c. So I can say this is going to give me e to the tangent theta plus c. Now, hopefully you're thinking you didn't like that problem. I'm not crazy about it either. Let's put a definite integral on one of these. What if I say I want to integrate x, and we'll come back to trig functions in just a second, x times 3x plus 9 to the 10th, and I want to integrate this from when x is 2 to when x is 10 with respect to x. We've got to put that. So when I look at this, I can say method of substitution, the group to a power. There's no way I want to say 3x plus 9 to the 10th and try to expand that out and figure what it is. So I know that the obvious choice is to let u equal 3x plus 9. And then du is going to be 3 with respect to x. I don't see a 3 dx in there, so I'll put it. Times 3. On the outside, I have to do my 1/3. So that part's taken care of. In addition to that, I'm going to go ahead and change my limits of integration. It's not 2 to 10 if I'm going to put this in terms of u. So I'll say, okay, u evaluated at 2 is going to give me 3 times 2 plus 9. 6 plus 9 is 15. U evaluated at 10 gives me 3 times 10 plus 9, 39. So I can say this is equivalent to 1/3 the integral, not starting at 2, but starting at 15, going up to 39. Now, the only thing I have not accounted for yet, and I purposely did this, I'll show it in the next step, I haven't accounted for that x. I'll leave it in there. This group 3x plus 9 to the 10th is just u to the 10th. 3 dx is du. So now, just as with the earlier problems where we had this substitution, you say, well, I can get rid of the x now by going over here and saying, I know u is 3x plus 9. So if I want to solve for x, I can say u minus 9 is equal to 3x. So x is equal to u minus 9 over 3. Now let's do this one the more efficient way than what I did before. Before I said, hey, let's distribute that 3 up into this and call it 1/3 u minus. That's fine. It works. The more efficient way is if I leave it like this and I say, I have 1/3 the integral from 15 to 39. X is nothing more than u minus 9 over 3. I'll be multiplying that by u to the 10th du. So if I have a factor that has a 3 in the denominator, that's a constant. Just factor that 3 out. As a 1/3 in front, so I'll say I need to bring that 3 out. It's going to become a 1/9 in front. And then I have u minus 9 times u to the 10th du. So now in this step, I can say, well, this is going to be 1/9. And I'm probably showing more steps than you'd need to, but I want to make sure I don't lose you as much as possible. Inside here, this u to the 10th distributes. I get u to the 11th minus 9u to the 10th. Integrating with respect to u. So I can say, well, I'll have 1/9 times the group. The integral of the first term here, u to the 12th over 12. Minus the second term, it's going to become 9u to the 11th over 11. And we're evaluating that from 15 to 39. Ooh, that's going to be some ridiculously large numbers in there. So if I tried to evaluate this on the calculator, I'll say, okay, let x equal 39. 39 is x. And then I'll say, okay, so what is x to the 12th divided by 12 minus 9x to the 11th divided by 11? Woo! Yeah, big number. So I would say, okay, that's huge. If I wanted to try to handle that all at the same time, I guess, I could say, from that I'll subtract 15 raised to the 12. I'll say minus the group. You won't have any that have this large of answers in your work. 15 to the 12th divided by 12 minus 9 times 15 raised to the 11th divided by 11.
You didn't divide by 12.
Yes.
Yeah. You didn't divide by
Oh,
12.
15 to the 12th divided by 12. Thank you. Yeah, now minus 9 times 15 to the 11th divided by 11. Okay, this should be right. It's still a huge number. And I'll divide that by 9. So the answer I'm getting in scientific notation, you could just say this is approximately 8.578. Times 10 to the 16th power. Now, what if you're thinking, I bet the answer shouldn't have been that large? Whoa, you're wrong. So this is one I would definitely want to check. So I'd say, I want to integrate the original function here, which was the integral 2 to 10 of x times 3x plus 9 to the 10. So I'll say math 9, x times the group 3x plus 9 raised to the 10th. That's my function. I'm integrating with respect to x, starting when x is 2, going to when x is 10. And we get the same answer.
When I typed in that function, I did it the other way. I just did it, I put the 10 in the formula that I got, and I didn't subtract it when I put the 2 in. And before I subtracted, I still got that exact answer.
Are you sure? I bet what it was is whenever I subtracted mine, I didn't notice any difference when I subtracted off the 15 either. Is it exact all the way on out?
Well, I got 8.578 either way, and I still haven't subtracted it.
I think it's just because the other is so small in comparison, it's not going to knock it off. But that would concern me a bit. But I think it's just because the second number evaluated in is so small. So 39 to the 12th power overpowers 15 to the 12th power by so much. It doesn't matter that you're subtracting it off in the long run. Okay. Let's see. Got a little bit of time left. Let's look at another trig problem. So I'm on problem 13. I want to look at the integral from 0 to pi over 2 of the cosine cubed of x times the sine of x dx. Again, in this one, it should not take you even a second to guess what u is. There is no way on earth I would let u equal the sine of x here. Because if u is equal to the sine of x, then du is the negative cosine, du would be the cosine of x dx. I don't have the cosine of x dx, I'd have the cosine cubed. So I said that would not work. But would it work if I let u equal what's inside of this group q? Say, yeah, if I let u equal cosine x, then du is the derivative of cosine negative sine of x with respect to x. That I do see as a factor. I have sine of x dx. I need a negative, so I can always factor in any constant factor. I'll multiply by a negative 1, multiply the outside by a negative 1. That will work. At this same time, I'm going to go ahead and change my limits of integration. My lower limit was 0. So I'll say, well, 0 is going to become cosine of 0 is 1. My upper limit of integration was pi over 2. When I evaluate u at pi over 2, I get cosine of pi over 2. We know that's the x value in the unit circle straight up. That's 0. So instead of evaluating from 0 to pi over 2, I'm now evaluating from 1 to 0. So I'll say, well, this is the negative of the integral, starting at 1, ending at 0, of what's inside. Well, cosine cubed becomes u cubed. All of this becomes du. And now, if you wanted to, you could say, I don't like the looks of that, John. Could you call it the positive integral from 0 to 1 of u cubed? Of course you could. That would look even better. I'm going to stick with this and say this is equal to the negative of, this is u to the 4th over 4 when we integrate it, evaluated from 1 up to 0. So you'd say, well, this is the negative of, when I evaluate it at 0, I get a 0, minus the lower limit of integration. When I plug in a 1, I just get 1/4. So I get the negative of a minus 1/4, positive 1/4. We got it. Hopefully you're thinking we haven't done any tough problems yet. I think we'll have plenty of time to do the hardest problem of the day. Be a good one to end on, and I think it will take at least 10 minutes to do it.
Why would you end with that?
I want to look at the following with you. This will be a warm-up to the hardest problem. So, easy or hard problem. I'm afraid to do the hard one first. So, easy or hard problem. And the good thing about the easy or hard problem is it gives us another trig function. So, what if I give you the cotangent of x times the natural log of the sine of x? And so this one's not bad at all. Whenever you think about this one, though, you'd say, well, what should be the obvious trig substitution in this one? Well, okay. So if I try the sine of x, I could say, well, if I say u is equal to the sine of x, then du is equal to the cosine of x dx. Do I have a cosine x dx in there? I do! Yes! So what you have to do is you say, okay, cotangent is nothing more than cosine x over sine x, yes, times the natural log of the sine of x dx. So I can say, okay, everything I'm going to circle becomes du. So cosine x dx, that becomes du. So I'm going to have the integral, all this is going to become a 1 in the numerator. I still have a sine of x in the denominator, but I say, well, sine of x is u, so I'll get 1 over u times the natural log of u du. And I'll even write that as, well, this is the natural log of u over u du. So we haven't put it into a problem where we can integrate yet, but hopefully you recall we worked a problem like this earlier in the day. What happens in this case? I can say, well, it's not in a form where I can integrate, but if I use substitution one more time, it will be. Because I can say, let w, so this is double substitution. We will work problems that require triple substitution later on. So I'll say, okay, let w equal the numerator. So if w is the natural log of u, take the derivative of w. The derivative of w is going to be 1 over u with respect to u. And I say, do I see a 1 over u with respect to u in there? Yes. All of that becomes dw. And I can say, well, my numerator is just w. So this is equal to the integral of w dw. Which we can then say, well, the integral of w is just going to be w squared over 2, 1/2 w squared plus the constant of integration. Hopefully you're thinking, I would never want to leave my answer in w when it's supposed to be in terms of x. Of course not. I'll go back and back substitute. If you're able to do it all in one step, that's fantastic. I'm going to do it one step at a time and say, okay, but w is equal to the natural log of u. So I can say this is 1/2 the natural log of u, quantity squared, plus c. But I'm not done with that, because now I know u is equal to the sine of x. So this is equal to 1/2 the natural log of the sine of x, all of that quantity squared, plus c. Is that one okay? All right. Now, that was my easier hard problem. The hard problem. If you can follow me on this one, you are in fantastic shape. Let's see. Let's say I ask you to integrate. I'll say x on the square root of 5 minus, the square root inside the square root of 4 minus x squared dx. So I can say the layers in this problem is what makes it fun. Oh, there's some type of gum. The layers is what makes it good. Kind of the same thing here. So you say, okay, in this case, if I let u equal 4 minus x squared, I can say, well, du would be negative 2x dx. That's not too bad. So I can say, I need to see a negative 2x dx in there. I already have an x dx, so I'll just say, well, I need to multiply by a negative 2 then. And I'll multiply on the outside by a negative 1/2. I already know this is not going to be in a form where I can integrate, but it is an improved form. So I'll go ahead and write it. It's going to be negative 1/2 the integral. X, negative 2 dx, all of that is du. But I'll still have the square root of 5 minus the square root of u du. I would argue this is better than what I started with. Still not integrable. So I say, do this again. So I'll say double substitution, let w equal what's inside the group? 5 minus u. Or sorry, 5 minus the square root of u. So I can say, well, dw, and so I'm going to rewrite w first. W is 5 minus u to the 1/2 power. So dw would equal, the 1/2 comes down in front, negative 1/2 u to the negative 1/2, which means it's going to be negative 1 over 2 on the square root of u du. And I should have put that right here too, du. So I can say, well, do I see a negative 1 over 2 on the square root of u du in there? Absolutely not. I don't. That's okay. So here's what I'm going to do. I can say, if I don't see any way to algebraically make that in there, here's the technique we're going to use. I know that dw is equal to negative 1 over 2 on the square root of u du. That's true. If I don't see a way to get that in there, and I know I have a du in there, instead of solving for dw in terms of du, turn it around and say, well, solve for du in terms of dw then. And so I'll say, okay, multiply by 2 on the square root of u on both sides, and a negative 1 on both sides, and I'll get 2 on the square root of u negative times dw is equal to du. So I can say, I know this would take the place of du in there. And I can say, well, is that going to help out? Actually, it will. Because now, in fact, I'll go ahead and write it in here. All of this is going to become the square root of w. And then in the place of du, I can put negative 2 square root of u dw. The only thing that's bugging me is that right there. No problem. Why? I have a function that's combining w and u right here. So I need to solve for what is the square root of u. I'll go right here and say w equals 5 minus the square root of u. So w minus 5 is the negative square root of u. So the positive square root of u is 5 minus w. So I go back into my problem, and I'm going to do one other thing at the same time. I'm going to factor this negative 2 as a factor on the inside. What happens when I factor that negative 2 to the outside? What's in front? Just be not a negative 1, but a positive. So it completely cancels out that in front. Negative 1/2 times negative 2 is positive 1. So I'll say this becomes just 1 times the integral of the square root of w. Remember, this negative 2 is gone. And I've shown that the square root of u is equal to 5 minus w dw. We have used double substitution along with algebraic simplification to get this to a part where we can evaluate it now. So I'll say this is the integral of 5, I'll call it 5w to the 1/2 minus w to the 3 over 2 dw. So I can say, integrating the first term here, I'll get 5w to the 3 over 2 times 2/3. 5 times 2/3 is going to give me 10/3 w to the 3 over 2. When I integrate my second term, w to the 3 over 2 changes to w to the 5 over 2. Multiply the front by 2/5 minus 2/5 w to the 5 over 2 plus your constant of integration. I can say this would be my answer in terms of w, but of course we want to put it back in terms of x. So I would take this answer, first put it back in terms of u. So I'd say, well, w is equal to 5 minus the square root of u. So this would be 10/3 the group 5 minus the square root of u inside of a square root raised to the 3rd power minus 2/5 on the square root of 5 minus the square root of u raised to the 5th plus c. And then you say, well, okay, that's back in terms of u. The final answer needs to be back in terms of x. The only thing I have to do is say, well, u was the group 4 minus x squared. So this original gorgeous problem that I warned you was tough is 10/3 on the square root of 5 minus, not the square root of u, but the square root of 4 minus x squared. And it's that group cubed. And then we can say, well, we know it's minus 2/5, the square root of the same group, 5 minus the square root of 4 minus x squared. And this time, the quantity is to the 5th. That would be our original problem.
New set of
It's not. Okay, so I will stop with that today. Give you something to think about. D2L was down when I tried to post the homework solutions. I'm sure it's up by now. Yeah. So I'll go back to my office and immediately scan in my section 5-6 homework, all 7 pages of it. Is our exam next Wednesday?